So let's start from where we left off. We've been tasked with separating compounds to be able to identify and quantify those compounds. We've already determined that we can use polarity to separate compounds. What else can we use? Well, we can also observe that temperature may be a physical parameter that we can use to separate components. Let's take a look. A boiling pot on a stove can be used as an empirical experiment. It's simple to observe and understand that the higher we turn the flame, the more violently the liquid boils in the pot. At high temperatures, the liquid has enough vapor pressure to push the lid off of the pot. So somehow, temperature and vapor pressure are related. The higher the temperature, the higher the vapor pressure. And we can observe that different components react differently. That is, we can observe that different components boil at different temperatures. Or said another way, different components produce different vapor pressures at similar temperatures. And it is this difference that we can take advantage of. So let's put this new observation in the form of an equation. The vapor pressure of a component is directly proportional to the temperature of that component. We can use that relationship, but we have to understand it in a more precise way. In other words, in order to use the relationship, we have to be able to predict the relationship. The Clausius Clapeyron Equation provides us with what we're looking for. It provides us with a more precise, more predictable relationship between vapor pressure and temperature. Looking at the equation, we can see that the only variables are vapor pressure and temperature. The other components of the equation are constants and do not change with the vapor pressure or the temperature. The gas constant does not change with the chemical compound. It is the enthalpy of vaporization that changes with the chemical compound, and we can use that with the vapor pressure and temperature as a means of separating chemical compounds. The delta H sub VAP is the change in the enthalpy of vaporization. It is essentially the energy required for a chemical compound to go from a liquid to a gas. The definition is a bit more complicated than that, so if you want more specifics, a Google search will lead you in the right direction. But for us, it is a constant that we can look up in a table. Here, the significance is that it is constant for each chemical species. To apply this equation for our purposes, we need two more steps. One step is to integrate over 2 points. In other words, we need to convert the equation to handle 2 points on the vapor pressure temperature curve, from P1 T1 to P2 T2. The last step is to arrange the equation to solve for one variable, P2. Now that we can solve for P2, we can generate graphical curves which will help us understand the relationship between vapor pressure and temperature. If we plot the vapor pressure versus the temperature, we get a curve that illustrates the change in vapor pressure with the increase in temperature. As predicted by the equations, the vapor pressure increases as the temperature increases. As the delta H sub VAP increases, the base value of the curve moves out on the temperature axis, and the shape of the curve remains similar from compound to compound. And, as you would expect, the larger the compound in the same family, the more energy it takes to get it from a liquid to a gas. The enthalpy of vaporization is more. So it looks like we can use temperature to separate compounds. According to Wikipedia, the distillation of petroleum was described in detail by Persian chemists in the 9th century. So heat has been used to separate chemicals for quite some time. When you look at a crude oil distillation column, you'll notice that it has sections. Each section is controlled at a different temperature. The temperature of each of these sections is determined by the relationship that the Clausius Clapeyron Equation defines. The equation defines the relationship between the temperature and vapor pressure of classes of chemical compounds. Looking inside the crude oil distillation column, you'll see there are sections that isolate different fractions of the crude oil. Each section is equilibrated to a particular temperature, a temperature that is specific for the range of chemicals that are to be isolated from the crude oil. The refining of crude oil using a distillation column is where HPLC and chromatography in general gets one of its core concepts, the concept of plates. Each section of the crude oil distillation column has an apparatus called a plate. In this version, a plate consists of a pair of column trays populated with bubble caps. The purpose of these column trays is to collect the distillate from the crude oil. The distillate is then siphoned off and collected. One consequence of this process is the ability to add more plates, resulting in more sections to the crude oil distillation column. This will provide more crude oil fractions, so more plates for more crude oil fractions. This is a continuous process. Crude oil is heated, distilled, and collected. An easy way to illustrate this process is to use a graph to show the buildup of each crude oil fraction as it is collected. This demonstrates the basis for the theoretical separation of components in chromatography, or chromatographic peak resolution. The first commercial oil refinery in the United States started operation in July of 1860 in Titusville, Pennsylvania. 10 centuries after the distillation of crude oil was described by Persian chemists. The distance between the first operational oil refinery in the United States and the routine use of HPLC was much shorter. HPLC, as it has come to be employed today, was developed in the mid to late 1970s. Initially, HPLC was an abbreviation for high-pressure liquid chromatography, but today it's known as high-performance liquid chromatography. In HPLC, the chromatographic peak will be your central focus. The quality of your chromatography is demonstrated by the peak shape. The identity of the components is determined by the peak retention time, and the concentration of your components is determined by the height or the area of the chromatographic peak. The number of theoretical plates of a chromatographic column is an indicator of the quality of the column. The equation determining the number of theoretical plates has the ratio of the peak width to the retention of the peak as its core parameter. That ratio is squared and is then multiplied by 16. If, for some reason, it isn't possible to determine the peak width at the baseline, there is an alternative equation for determining the number of theoretical plates using the width at its midpoint. To go through the parameters of the equation, T sub m is the holdup time, or dead volume of the column. This is the time it takes for the solvent to travel from the beginning of the column to the end of the column. T sub 1 is the retention time of the peak. T sub 2, the adjusted retention time, is arrived at by subtracting the holdup time, T sub m, from the peak retention time, T sub 1. The width of the peak, W, at the baseline is computed by drawing a straight line from the top of the peak to the baseline on both the upward and downward slopes of the peak. The peak width is arrived at by measuring this distance. If for some reason it isn't feasible to measure the peak width at the baseline, the peak width at the middle of the peak's height, W subscript 0.5, can be used in equation 2. Either of these equations results in n, or the number of theoretical plates on this column. As you can tell by the equations, the more narrow the peak, the larger the number of plates. And the final equation, number of theoretical plates n, divided by L, the length of the column, results in the HETP, or height equivalent to a theoretical plate. This term provides for a point of comparison for all chromatographic columns. The higher this number, the more separating power of the column. An 8 mm HPLC column with 100,000 theoretical plates results in a column with an HETP of 12,500, whereas a 4 mm HPLC column with the same number of plates is a column with an HETP of 25,000. If an HPLC method is used by various entities across multiple environments, the HETP can be used to define a minimum criteria to assure the chromatographic column can produce the necessary component separation. Overlapping peaks can impact both the accuracy of the peak area computation and the peak retention time. If you are developing a qualitative analytical method to be used in various environments, it may be necessary to stipulate in the method definition a minimum resolution for 2 or more adjacent peaks to assure a successful analysis. Baseline separation is always best. Baseline separation is defined as the condition where the detector line returns to the baseline between the 2 peaks. By the resolution equation, baseline resolution is typically considered achieved when R is equal to 1.0. As peaks of the same width move closer together, the resolution computes to be less than 1.0. Keep in mind that the resolution will depend on the HETP, and the HETP is dependent on the column and its number of theoretical plates.